In the 7th chapter of our course on linear systems theory, we will look at the eigenstructure of matrices. Let's begin by looking at where we are in this chapter and where we are going in the next few chapters. So in the previous chapter 6, we have introduced linear maps between two vector spaces V and W. Starting with this chapter, chapter 7, we will look at a special type of linear maps, namely maps whose domain and codomain is the same vector space V. And this special type of map will be referred to as a linear operator. So for the linear operator, the domain and the codomain are both the same vector space V. As we know by now, on finite dimensional spaces, this corresponds to the set of square matrices, so matrices in C n by n. In chapter 7, we will first take a look at their basic mapping properties, in particular at eigenvalues and eigenvectors, which are hopefully familiar to most of you already. Chapter 8 then looks at the combination of multiple such mappings, and chapters 10 and 11 will focus on special cases. We begin this chapter with definition 7.1 of an invariant subspace. So let L be a linear operator, which in terms of this course means that its domain and codomain are the same vector space V. A subspace of V is then called L invariant if, for any vector x in the subspace, we have that also L of x is an element of the subspace. So basically, by applying L to any vector of the subspace, I will not leave the subspace. Clearly, the entire vector space V and also the point 0 are trivial examples of L invariant subspaces. Moreover, it's also trivial to see that the range space of L is an L invariant subspace. If for a given linear operator L, we have an L invariant subspace S, then we can define the restriction of the operator L to the subspace S, which we denote like this, and which is another linear operator now mapping from the subspace S into the subspace S, and it's just defined as behaving exactly like the linear operator L, but just for any value x in the subspace S. And it's easy to verify that the restriction of a linear operator to such a subspace is again a linear operator. All that needs to be done for this is to check the linearity properties of the operator L restricted to S, which follow immediately from the linearity of the operator L. Of particular interest are L invariant subspaces which have the dimension 1, and this exactly leads to the definition of eigenvalues and eigenvectors of a linear operator. On this slide, we have definition 7.2 of the eigenvalues and eigenvectors of a general linear operator between two abstract vector spaces. So if there exists a non-trivial vector x in the vector space and a scalar lambda in the field such that L of x equals to the lambda multiple of x, then lambda is called an eigenvalue of L with the associated eigenvector x. Based on this fundamental definition of an eigenvalue and an eigenvector of a linear operator, we have some further terminology listed in definition 7.3 that we will make frequent use of. So let L be a general linear operator, then A, the spectrum of L, written as spec of L, is defined as the set of all eigenvalues of L. B, the eigenspace of L, is defined as the span of all eigenvectors of the linear operator L. And finally C, the spectral radius of the linear operator is a positive real number, or possibly infinity, which is denoted by rho of L, and it's defined as the supremum of the absolute value of all eigenvalues. So all values lambda in the spectrum of L. You're certainly familiar with the definition of eigenvalues and eigenvectors for matrices from your undergraduate linear algebra course. However, the definition we make in this course here is much more general than this, because it's defined for operators on abstract vector spaces. So that includes also operators, for instance, on sequence spaces or function spaces. And to get a better grasp of the concept of eigenvalues and eigenvectors, it's very helpful to look at operators on other type of vector spaces. And that's exactly what we're going to do in the examples here. And we start by asking for the eigenvalues and eigenvectors of the left shift operator, sigma 1, which maps from the sequence space L infinity to L infinity, and whose definition was introduced in the previous chapter. So recall that sigma 1 of a sequence is another sequence that's shifted by one element. So how can we determine the eigenvalues and eigenvectors of the left shift operator? Well, we use the condition stated in definition 7.2 for the eigenvector and eigenvalue, where in this case the eigenvector is of course a sequence, and the condition reads as sigma 1 of the eigenvector must be equal to lambda times the eigenvector. Substituting the value for sigma 1 of the sequence, we obtain this expression, which we can now break down into the single elements of the sequence. And this yields for the first element of the sequence of each side that x2 must be equal to lambda times x1. For the second element of each side, it yields that x3 equals to lambda x2. So by the above, this equals to lambda squared x1. Then we continue with x4 is equal to lambda times x3. So hence it's equal to lambda cubed times x1 and so on. So we may conclude that for any value lambda in C, the sequence lambda to the k-1 times x1 is an eigenvector that corresponds to this eigenvalue lambda. And that's for any choice of x1 in C, which is not surprising because we know that if a vector is an eigenvector, then also any scalar multiple of this vector is an eigenvector. And this x1 here appears in all the elements of the sequence, so it's just a scalar multiple of the sequence lambda to the k-1. However, this eigenvector, or any scalar multiple of it, is only in L infinity, so it's only absolutely bounded if and only if the value of lambda is in absolute value less than or equal to 1. Therefore, we can conclude that the spectrum of the left shift operator is equal to the unit disk in the complex plane. And the corresponding eigenvector for each lambda in the spectrum of sigma 1 is given by this sequence. So we have this result stated here. And next, we also want to determine the eigenvalues and eigenvectors of the right shift operator, sigma -1, which maps from L infinity to L infinity, and which is defined, as we remember from the previous chapter, as sigma -1 of a sequence equals to the sequence that's defined by a0 as the first element, and then followed by all the elements of the sequence. In order to find the eigenvalues and eigenvectors, we again apply the condition of definition 7.2 for a sequence to be an eigenvector and lambda to be an eigenvalue of the right shift operator, namely sigma minus 1 of the sequence must be equal to lambda times the sequence. Substituting the definition of sigma minus 1 of the sequence yields the sequence 0, x1, x2, and so on, which must be equal to lambda times the sequence x1, x2, x3, and so on. This implies that we must have equality for all the elements of the sequence. So first 0 must be equal to lambda times x1, then x1 must be equal to lambda times x2, x2 must be equal to lambda times x3, and so on. The first condition implies that either lambda must be equal to 0 or x1 must be equal to 0. Let's first look at the case where lambda is equal to 0. If that's the case, then all the following elements, so x1, x2, and so on, they must all be 0. And second, let's look at the case where x1 equals to 0 and lambda is non-zero. If lambda was 0, we would be back to the first case. So now lambda is non-zero and x1 is 0, which means that x2 must be equal to 0, x3 must be equal to 0, and so on. So we conclude that lambda must be equal to 0, and also the eigenvector must be equal to the 0 sequence. But according to definition 7.2, an eigenvector may not be 0. Therefore, it follows that the right shift operator has no eigenvalues, or in other words, the spectrum of the right shift operator is the empty set. And that's again what's stated here. As a third example, we determine the eigenvalues and eigenvectors of the differential operator, which we denote by a capital D, and which maps from the space of infinitely continuously differentiable functions to the space of infinitely continuously differentiable functions. And it maps any function f of t in that space to its derivative, so d dt f of t. Here, the set of infinitely continuously differentiable functions means that any function in that space has infinitely many derivatives, and all of these derivatives are continuous. It's easy to verify that this set is in fact a vector space. Again, to find the eigenvalues and eigenvectors of this operator, we write down the condition for a vector f of t to be an eigenvector and a value lambda to be an eigenvalue of the operator, which according to definition 7.2 is that d of f of t must be equal to lambda times f of t. Substituting the calculation rule for the differential operator, we see that in this case the eigenvalue problem leads to a simple differential equation whose solution we all know by heart, namely f of t equals to e to the lambda t. Since this works for every possible value of lambda in C, we can deduce that the spectrum of the differential operator equals to the entire complex plane, and the corresponding eigenvector to an eigenvalue lambda equals to e to the lambda t. So the result is stated here again. The final example is about determining the eigenvalues and eigenvectors of the Volterra operator, which is an operator on the space of continuous functions on the interval from 0 to 1. And as we have seen in chapter 6, it's defined by mapping a continuous function f of t to its primitive function. So the image of f is given by the integral from 0 to t of f of tau d tau. And the solution to this example will be a part of exercise sheet 8. The result, however, is already stated here, namely the spectrum of the Volterra operator contains exactly one eigenvalue, which is equal to 0. So your job in the exercises will be to prove this equation. Next, we make the step from general linear operators on abstract vector spaces to square matrices, which represent linear operators from Cn to Cn. As you probably know from undergraduate linear algebra, the definition 7.2 of eigenvalues of a linear operator breaks down for the eigenvalues of A in terms of the roots of its so-called characteristic polynomial. And that characteristic polynomial, denoted with chi of A of S, is given by the determinant of Si minus A, which, if it's spelled out, corresponds to a polynomial of order n with some coefficients alpha n minus 1 to alpha 0. So what we want to show by lemma 7.4 is that the general definition 7.2 of eigenvalues and eigenvectors leads to the roots of the characteristic polynomial in case where the linear operator is given by a matrix. So for the proof of lemma 7.4, we start with definition 7.2 of an eigenvalue lambda of the matrix A. It states that there must exist an eigenvector x in Cn with x not being equal to the 0 vector, such that Ax equals to lambda x. By bringing Ax to the right-hand side of the equation, this is equivalent to there exists a vector x, x being non-zero, such that lambda x minus Ax, or in brackets lambda I minus A times x, equals to 0. By looking at this condition more closely, we see that this means exactly that there must exist a non-trivial vector x, which is in the null space of the matrix lambda I minus A. And by lemma 6.13, this means that the matrix lambda I minus A has to be not invertible, or in other words, it is singular, and therefore its determinant has to be 0. Hence, we have shown that definition 7.2 of an eigenvalue is equivalent to this condition in case where the linear operator is given by a matrix. The characteristic polynomial follows simply by calculating this expression, and it's clear that this will lead to a polynomial of degree n. A few more remarks about eigenvectors. First, the intuitive definition of an eigenvector is that this is a vector whose direction is invariant under the action of A. In other words, if I apply A to the eigenvector, it will change its length, but it will not change its direction. Second, clearly, if x is an eigenvector associated with some eigenvalue lambda, then so will be any scalar multiple of x. However, we will not count scalar multiples of an eigenvector as a different eigenvector. Instead, all scalar multiples of an eigenvector x are considered as the same eigenvector. Next, we have theorem 7.5, which gives two very important and useful formulas for the eigenvalues of a matrix. So if A is an n by n matrix, it has n complex eigenvalues as the roots of the characteristic polynomial by the fundamental theorem of algebra, and these n eigenvalues satisfy A, the product of these eigenvalues equals to the determinant of A, and B, the sum of these eigenvalues equals to the trace of A. For the proof of theorem 7.5, we start with part A, and we begin with the observation that the characteristic polynomial of A, chi A of S, is given by the determinant of Si minus A, according to lemma 7.4. Now let lambda 1 through lambda n be the eigenvalues of A, in other words, the roots of the characteristic polynomial chi A of S. Then the characteristic polynomial can be factorized as S minus lambda 1 times S minus lambda 2 and so on up to S minus lambda n. Equating our two formulas for chi A of S yields that the determinant of Si minus A is equal to the factorization of the characteristic polynomial. Now this formula holds for all complex values S, so in particular we can put S to 0 and we obtain exactly the formula that we want to prove. For the proof of part B, we again express the characteristic polynomial chi A of S in two different ways. First, in a factorized form, as we did in part A. And now we start to multiply these terms in order to get an explicit expression for the characteristic polynomial. However, we only think about the first two coefficients of the highest powers of S, namely Sn and Sn minus 1. So obviously the coefficient of Sn will be 1 because this term will only appear once by multiplying all the S terms in the brackets. The second coefficient, alpha n minus 1 of the power S to the n minus 1 is given by minus lambda 1, minus lambda 2, and so on up to minus lambda n. And that's because we always choose from one bracket, for instance the first one, the minus lambda 1, and from all the other brackets we choose the term S. And the same works if we choose for the first bracket the term S, and the second bracket minus lambda 2, and then for the rest of the brackets always the S. So if we do this for all of the brackets, this is the expression that we get for the coefficient alpha n minus 1 of the power S to the n minus 1, and all the other terms that result from multiplying out this factorization will have a lower order, so S to the n minus 2 or even lower, and we don't care about these coefficients. They are very complicated expressions of the lambdas, but again, for the purposes of this proof, we don't care about what they exactly look like. Secondly, the characteristic polynomial chi A of S is also given as the determinant of Si minus A, which, if we write this down explicitly, looks like the determinant of a big n by n matrix, where each element is minus the corresponding element of A, and we have additionally plus S for each of the diagonal terms. Now, by using the minor expansion formula to calculate the determinant of this big matrix, this implies that chi A of S can be written as the product of S minus A11 with S minus A22 and so on down to S minus A and n plus a polynomial of degree n minus 2. And you should check for yourself that if you expand, for instance, by the rows of the matrix, all the other expansion terms that you will get have a maximum degree of n minus 2. Now, by the same argument as above, we can multiply out this factorization and only look at the coefficients of the two highest powers of S, namely Sn and Sn minus 1. If we do this, clearly we get a 1 in front of the Sn, because we are choosing always the S term in all of the brackets. And for Sn minus 1, we're choosing once, for instance, minus A11, and then S in all the others. And in a similar way, we choose S for the first one, then minus A22, and then S in all the others, and so on. So we get this expression here for the coefficient of Sn minus 1. And again, we don't care about all the terms that result from this factorization and which have a power of S to the n minus 2 or below. and we just mix them into the residual polynomial of degree n-2 at the end of this sum here. But since the residual polynomial only contains powers of s from s to the n-2 and below, this implies that this term in the bracket here must be equal to the coefficient alpha n-1 of the power s to the n-1. Now, all we need to do is equate the two results for the coefficient alpha n-1 that we have obtained above, and we get to the equation minus a11, minus a22, and so on up to minus ann is equal to minus lambda 1, minus lambda 2, and so on up to minus lambda n, where clearly the left-hand side is equal to minus the trace of a, and the right-hand side is equal to minus the sum of the eigenvalues of a. Now for some remarks about eigenvalues, and in particular about repeated eigenvalues. As already mentioned, by the fundamental theorem of algebra, the characteristic polynomial of an n by n matrix has n roots, and therefore A has n possibly repeated eigenvalues. If A happens to have n distinct eigenvalues, then it does have a full set of n linearly independent eigenvectors. This fact is stated in theorem 7.7 that we will look at in just a minute. If A has less than n distinct eigenvalues, meaning that there are some repeated roots of the characteristic polynomial, then there may be or there may not be a full set of n linearly independent eigenvectors of A. Based on these remarks, we make the following definition 7.6. An n by n matrix A is called simple if it happens to have n distinct eigenvalues, and it is called semi-simple if it may have repeated eigenvalues, but it still has n linearly independent eigenvectors. In the next theorem, 7.7, we establish the famous Jordan form, which probably most of you have seen before, and it states the following. Let A in Cn by n be a simple matrix with distinct eigenvalues lambda 1 through lambda n, and associated eigenvectors x1 through xn, which are here defined as column vectors. Then we can define the n by n matrices T, which consists of the stacked up eigenvectors x1 through xn, and the diagonal matrix lambda, so that's a capital lambda, which has all the eigenvalues of A, lambda 1 through lambda n, on its diagonal. Then there are three statements of this theorem. A, the eigenvectors x1 through xn are linearly independent. So what's given in the assumptions is that A is a simple matrix, which means that the eigenvalues are distinct. But now the statement A says that this means that the eigenvectors are linearly independent. B, the matrix T is invertible. And C, by computing T inverse AT, we get the diagonal matrix lambda, which has all the eigenvalues of A on its diagonal. Now let's look at the proof of theorem 7.7, beginning with part A. For the sake of a contradiction, here we assume that the set of eigenvectors x1 through xn is linearly dependent. By definition, this means that there exists a set of scalars alpha 1 through alpha n, which are not all zero, such that the linear combination alpha 1 x1 plus alpha 2 x2 plus and so on up to alpha n xn equals to 0. Because at least one of the scalars, alpha 1 through alpha n, is non-zero, without loss of generality, we may assume that alpha 1 is non-zero. And that's because the ordering of the eigenvectors x1 through xn is arbitrary, so we may always reorder those eigenvectors such that x1 is the one that carries the non-zero scalar. Now, if alpha 1 is non-zero, this means we can solve this equation for the eigenvector x1, and we get x1 is equal to the sum of k from 2 to n of alpha k divided by alpha 1 times xk. Now we define an n by n matrix that we call M as follows. So M equals to lambda 2i minus a times lambda 3i minus a, and so on up to lambda n minus 1i minus a times lambda ni minus a. Now we multiply both sides of this equation with the matrix M and show that the left-hand side, so mx1, and the right-hand side, so m times this sum, are not equal, which establishes the contradiction. First, for mx1, we can substitute the definition of m to obtain this expression, and we can now begin to multiply x1 into this first matrix in brackets here, where we see that lambda n times identity times x1 is equal to lambda n times x1, and ax1 equals to lambda 1 times x1, because x1 is the corresponding eigenvector to the eigenvalue lambda 1. Now, since lambda n and lambda 1 are both scalars, we can write this bracket here as lambda n minus lambda 1 times x1. And we can pull this scalar in front of the entire expression. Then we can play the same trick again by multiplying x1 into the second matrix in the brackets here, where similarly to the above, we see that the first term equals to lambda n minus 1 x1, and the second term equals to lambda 1 x1. So again, by pulling out the scalar lambda n minus 1 minus lambda 1 and pulling it in front of the entire expression, we end up with this expression here. And you can already see where this is going. We can continue this with lambda n minus 2 times I minus a, and so on through all of the matrices here. And what we will end up with is the following: lambda 2 minus lambda 1 times lambda 3 minus lambda 1, and so on up to lambda n minus lambda 1 times x1, where, and this is important, the entire expression that we obtained here has to be non-zero, and that's because we have distinct eigenvalues. So lambda 1 is not equal to lambda 2, lambda 1 is not equal to lambda 3, and so on up to lambda 1 is not equal to lambda n, and moreover, the eigenvector x1 is non-zero. Second, we also calculate the expression of m times the linear combination of eigenvectors from k equal 2 to n, which can also be written like this. Note, however, that all of these expressions mxk are equal to 0 for k equals to 2, 3, and so on up to n. Why is that the case? Well, we can follow the same procedure as above, starting with m times x2. By definition, this is equal to this expression. And now, if we go through the same procedure as above, what we get is lambda 2 minus lambda 2 times lambda 3 minus lambda 2 times and so on up to lambda n minus lambda 2 times x2. But now this first expression is obviously 0, and so mx2 has to be 0. Then we can do the same thing for mx3, which by definition of m equals to this expression. And if we again apply our procedure from above, we get that this is equal to lambda 2 minus lambda 3 times lambda 3 minus lambda 3 and so on up to lambda n minus lambda 3 times x3. This time it's the second factor, that's 0, and it follows that also mx3 equals to 0. By now it's obvious that whenever we take m times x4, m times x5 and so on up to m times xn, there will always be the corresponding factor in this factorization that's equal to 0. This means that we can repeat this argument, and what we get is that mx4 and so on up to mxn will all be 0. But if all of the expressions mxk for k equal 2 to n are all 0, this means that the entire sum here has to be 0, and hence we have a contradiction. Part B of the theorem, which states that the matrix T is invertible, follows immediately from lemma 6.13 together with part A, because the range space of the matrix T equals to the span of its columns, and the columns are linearly independent, so the range space equals to Cn, and therefore we have that T must be invertible. For part C, observe that by column-wise matrix multiplication, AT, which is by definition A times the matrix, which has the eigenvectors x1, x2, and so on up to xn as columns, is equal to the matrix AX1 in the first column, AX2 in the second column, and so on up to AXN in the last column. Because x1 through xn are the eigenvectors of A that are associated with the eigenvalues lambda 1 through lambda n, this matrix can also be written as the matrix of the column vectors lambda 1 x1, lambda 2 x2, and so on up to lambda n xn, which is in turn the same as T times the diagonal matrix lambda. Reading this from the beginning to the end, we get AT is equal to T lambda, and since by part B T is invertible, we get lambda is equal to T inverse AT. So this concludes our proof of theorem 7.7. Now some remarks about this theorem. If you compare this formula with the formula that we had for a change of basis on Cn, then you realize that the two look very much identical. So one can say that theorem 7.7 states that for a simple matrix A, there exists a change of basis such that A has a diagonal representation, namely by the operator lambda in the new basis. And this special basis, where the operator A becomes diagonal, is spanned by the eigenvectors of A, and it's called the eigenvector basis. Now, even though we proved theorem 7.7 for simple matrices, in fact, it holds analogously for the case where A is semi-simple, and you can try to prove this. For the case where A is not semi-simple, so it does have repeated eigenvalues, and it does not have a full set of linearly independent eigenvectors, the situation is significantly more complex. In this case, we consider the set of distinct eigenvalues, lambda 1 through lambda m, where m is of course less than or equal to n. And we define the numbers p1 through pm as the multiplicities of the corresponding eigenvalues lambda 1 through lambda m. Clearly, each of these numbers pi is an integer which is greater than or equal to 1. From lemma 7.4 and the fundamental theorem of algebra, it follows that the sum from I equal 1 to m of these numbers pi must equal to n. Now for this scenario that has just been described up here, where A is not semi-simple and not simple, there exists a corresponding result to theorem 7.7, which will be stated in fact 7.8 on the next slide. However, we will skip the proof because it is actually quite complicated and involved, and it does not offer any new fundamental insights. So we do not really gain anything by looking at the proof. It's just long and ugly. Nonetheless, it's of some importance to know what the Jordan form looks like in the general case, so where the matrix A is not necessarily simple or semi-simple. So for a general matrix A, there exists a non-singular matrix T, which can be used to perform a change of basis. And if we change the basis by taking T inverse AT, we get to the representation of the matrix A in the new basis, which is called lambda, and it looks as shown here. So it consists of a total of m so-called Jordan blocks. Remember from the previous slide that m represents the number of distinct eigenvalues of A. Moreover, each of these Jordan blocks, Ji, where I equals 1 through m, is of the dimension pi by pi, where pi, as defined on the previous slide, represents the multiplicity of the eigenvalue lambda I. These Jordan blocks Ji are again composed by a bunch of Jordan subblocks on their diagonal, where the number of subblocks is here denoted with ki, and these Jordan subblocks have the form shown down here, so they have the repeated eigenvalue lambda I on their diagonal and ones on their superdiagonal. So if we substitute these subblocks back into the Jordan blocks and the Jordan blocks back into the expression for lambda, we will get a matrix that has the eigenvalues of A on its diagonal, and then it has a bunch of ones in certain places on the superdiagonal, and otherwise the matrix consists only of zeros. To get a better illustration of what the general Jordan form looks like, we have here an example of a non-semi-simple and of course non-simple matrix A, which is defined as shown here, and it turns out that it has the eigenvalues lambda 1, lambda 2, and then the repeated eigenvalue lambda 3 equals to lambda 4 equals to 4. Of course, these eigenvalues can be computed by deriving the characteristic polynomial of A and then finding the roots of this polynomial. The eigenvectors that correspond to these 4 eigenvalues are shown down here, and as you can see, there are only 3 eigenvectors, x1, x2, and x3. So this matrix does not have a full set of 4 linearly independent eigenvectors. So A is not simple and not semi-simple. As you probably know from undergraduate linear algebra, in this case, x4 is replaced with what's called a generalized eigenvector. And this generalized eigenvector has to satisfy this condition. So instead of asking that A minus lambda 4I x4 being equal to 0, we ask that it should be equal to x3. And if we do this, we get this generalized eigenvector x4. Now collecting the 3 eigenvectors, x1, x2, and x3, as well as the generalized eigenvector x4 in one big matrix T, we obtain a matrix which is non-singular. And moreover, if we multiply A with T column-wise, we get to this expression here, which can also be stated as shown here on the right-hand side. And so we see that the matrix lambda, which is shown here, is not fully diagonal, but it has this single one up here on its superdiagonal, which comes from the generalized eigenvector x4. As you should verify for yourselves, the matrix lambda in this case consists of 3 Jordan blocks, which are shown in green here. In summary, we have the following main conclusions about the Jordan form. First, every n by n complex matrix has a general Jordan form where A can be written as T times lambda times T inverse for a non-singular transformation matrix T. Second, the transformation matrix T can be interpreted as a change of basis according to theorem 6.4. Third, lambda in the Jordan form of A is an n by n matrix with entries only on its diagonal and on its superdiagonal, and with the eigenvalues of A with their respective multiplicity as its diagonal elements. And fourth, if A happens to be a simple or semi-simple matrix, then moreover, lambda is a pure diagonal matrix, meaning that all other entries except on the diagonal are equal to 0. And finally, if A is not simple or semi-simple, then lambda may have entries of 1 in some places along its superdiagonal. All other entries are still 0. On the last slide in this chapter, we present some results that make a connection between eigenvectors and invariant subspaces, which were defined at the very beginning of this chapter in definition 7.1. And the first result is proposition 7.9, which states that if A is an n by n matrix and S is an A-invariant subspace, then the orthogonal complement as perp of S is a star invariant. For the proof of proposition 7.9, we pick any vector x in as perp. Now to prove that as perp is a star invariant, what we need to show is that a star x is also an element of as perp. To this end, observe that for any vector y in S, the following holds. First of all, ay is also an element of S, and that's because by assumption, the subspace S is A-invariant. Then the inner product of x with ay equals to 0, and that's because ay is in S and x is in as perp. Hence, the inner product of a star x with y, which by definition of the adjoint is the same as the inner product of x with ay, must also be equal to 0. But this implies exactly that a star x is perpendicular to y for all y in the subspace S. So therefore a star x is an element of S perp, and we have completed our proof. The next result is lemma 7.10, which states that if A is an n by n matrix and S is an A invariant subspace, then S must contain at least one eigenvector of A. And we omit the proof of lemma 7.10 here. And finally, we have theorem 7.11, whose proof is also omitted. And it states that if A and B are both n by n matrices, and moreover they commute, meaning that the product AB equals to the product BA, then A and B share a common eigenvector.